Rahul here again from MySlate, and here we will continue our discussion on derivatives, types of functions. Look at this example here on the top, y plus sin y equals cos x. Now here we want to find the derivative of y with respect to x, dy by dx. Here the problem is that we can't express y neatly in terms of x. So what do we do? Well, it's not too complicated. You simply take the derivative of every expression on the left hand side with respect to x and likewise on the right hand side. You take the derivative of both the sides with respect to x, every expression. And then what you try to do is you try to assemble all the terms which have dy by dx together on one side and take the dy by dx part common, so that you can get some kind of an expression for dy by dx through some simple manipulation. And whenever you have a denominator, you already know that you must specify the condition that it cannot take a value 0. Likewise, for the second example, we do the same. We take the derivative of every term on the left hand side and on the right hand side with respect to x, and then try to assemble all the terms with dy by dx on one side, and then try to express a neat expression for dy by dx, and also specify that the denominator, the condition when denominator cannot take a value 0. Okay. Now look at some functions where which can be expressed in parametric form. What do we mean by parameter here? Look at this example. As you know, you might recognize that this is the equation for a circle. Y is kind of an implicit function, but in the sense that we need to find dy by dx, right? We can express y in terms of x, but maybe there is an easier way to find dy by dx. We express this in polar coordinates. If you remember, circle equation could be expressed in terms of polar coordinates. That's what we do here. We express x as square root b times cos theta and y as square root b times sin theta, where theta is some kind of an angle with respect to x axis on the positive, on the counterclockwise direction. And you can judge for yourself that if you substitute these expressions on x and y, you will find that it satisfies this equation, right? So you can make that substitution. Now we need to find dy by dx. Well, it's pretty straightforward. You take dy by d theta on the numerator and dx by d theta on the denominator. You know that d theta would get cancelled and it would eventually become equal to dy by dx. But we do this because it's easier probably to calculate dy by d theta and dx by d theta, because we have got these simpler expressions. So that's what we do here. We take the derivative of y with respect to theta, x with respect to theta, and finally get the answer in terms of theta. But now we need to convert this in terms of x and y, because that's what we have in the original term. In fact, we need to convert this in terms of x if possible. Here we have written that as minus x by y, but ideally this y also should be converted in terms of x, and you can do that from here. You know that y can be written as b minus x squared and square root of that, and that's what you kind of substitute here for y to get the final answer. And again you specify that the denominator cannot be 0. I did not write that here, but you should not forget that. So what we have learned here is that when you can express both y and x in terms of a common parameter t, then it might be easier to find dy by dx in this manner, by taking dy by dt in the numerator and dx by dt in the denominator, and obviously specifying that the denominator can't be 0. Okay, so let us look at some more examples. We have a inverse trigonometric function here. Now y is sine inverse x, so x can be written as sine y, and this again could be seen as a kind of an implicit function of y, and therefore we take derivative with respect to x on both the sides, and then try to do some simple manipulation to get an expression for dy by dx, and that's what we do here. And we are able to get dy by dx as 1 by cos y, but eventually we should try to get this in terms of x, because that's what we have here. So we know that sin y is x. So, we convert y cos y in terms of sin y and then substitute x here to get this kind of an expression. And because we have this denominator, we specify that the condition that it can't be 0. Okay. So, for example, here x can't take a value -1 or 1, and this must be real. We are assuming that we are operating in the real domain. So, therefore, x must be a value between -1 and 1, not equal to -1 and 1, and neither less than -1 nor more than -1. Okay. Now, here we have all these neat formulae for the derivatives of these inverse trigonometric functions, and you can derive each of them in the similar way that we did for the sine inverse x. And the interesting thing to note here is that everywhere we specify the condition when denominator is not 0.